Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome back to another episode of the Reliability Matters podcast. I'm Mike Conrad. For those of you who are counting, this is episode number 113. I'm sure we're pretty much all aware of the world's oldest profession. We're not going to go there, but perhaps the world's second oldest profession is counterfeiting. Whenever a product is introduced, a counterfeit version soon follows. While the electronics industry has experienced counterfeit components from its inception, recent events such as the pandemic and the resulting supply chain shortages have fueled the counterfeit industry. Statistics by the Semiconductor Industry Association, or SIA, reveal that the counterfeiting of electronics parts in the U.S. alone costs the chip industry more than $7.5 billion every year. Again, that's just in the United States. According to new data from the ERAI, a global information board for counterfeiting, reports of counterfeit electronic parts are growing. Although it's difficult to put an exact figure on just how many counterfeit products are in circulation, estimates suggest that consumer and industrial businesses lose approximately $250 billion each year due to counterfeit parts. To talk more about counterfeit components and detection technologies, I invited Dr. Eyal Weiss, founder and CTO of Cyborg, to be my guest. Dr. Weiss received his PhD in electronic and computer engineering from BGU, Ben-Gurion University in Israel, as well as a master's in plasma physics and bachelor's cum laude in mechanical engineering from the Technion Israel Institute of Technology. He also worked as a researcher on pulsed plasma at Sorek Research Center, SNRC. He then worked as a technology department manager in the high-tech fiber optics industry. He was a technology manager at Lynx Photonics and then at XPlay, developing state-of-the-art silicon and optical chips production, packaging, and assembly production lines. He developed a new fiber pigtailing and packaging technology and built full-scale production lines utilizing this new technology. He returned to Sorek SNRC for about 15 years and served as an leading scientist of the R&D systems department. He built mass production lines and assembly lines for new sensors technology and developed their test equipment. He has twice received the prestigious Israel Defense Prize. In 2018, he founded and became CTO of Cyborg, developing electronic component qualification and authentication technologies. He is a member of the Israel Innovation Authority, Euramet, SAE, and IPC committees. He specializes in multidisciplinary technology development and has received significant awards and accolades in the fields of machine learning, plasma physics, optical assemblies, laser technology, and electromagnets. Dr. Weiss is an expert in technology development and manufacturing technology and has published over 20 peer-reviewed articles, 4 patents, and a book. And, most importantly, I'm happy to say, he's my guest on this episode of the Reliability Matters podcast. So without any further ado, let me introduce Dr. Weiss. Dr. Weiss, Eyal, how are you?
I'm great after this introduction. Wow.
Yeah, now we have to kind of let you down slowly. Yeah, exactly. That you are so accomplished that the bio alone is practically an episode. We should probably call that one episode 113, and now this is episode 114.
And my mother will be happy about it.
Show it to your mom. Exactly. Show it to your mom. She'll be very proud. Yeah. Do you have siblings? Do you have brothers or sisters?
Oh, yeah.
You have brothers or sisters?
One.
Yeah, you can show it to them. You can say, you can show it to them and say, okay, beat this. Yeah. Well, thanks again for being my guest on the show. Our topic of counterfeiting probably could not be more topical today, as counterfeiting, we've always had counterfeiting. As I said in the introduction, it's probably the world's second oldest profession. The moment the first thing was invented, the second thing invented was probably the counterfeit version of that. It's a very old profession, and in any economic climate, there's plenty of business going around for counterfeit. And in today's environment with supply chain issues and all that silly stuff that's going on right now, that certainly just fuels the counterfeit market. I think people are getting more desperate to secure parts. They're buying their parts from sources that may be unfamiliar to them and perhaps unscrupulous, and the door has been left open for counterfeiters to just walk in and almost invited to be walked in. So I think your timing for a business, although I'm sure you didn't plan it this way because it takes a little while to engineer a machine, your timing is very good.
And actually,
good time to be in your world.
My timing is actually a result of counterfeiting. The large project I was working on, which you described in the introduction, for 15 years, was a very, very large project. It was like a lifetime project, $1 billion project. I was working for 15 years with a team of 25 scientists, engineers, completely new technology. And when we deployed the system in the field after a few months, of course, after very rigorous testing, it started failing. And when it took us months for pure agony to find out what the reason was, we found out what caused the problem was counterfeit components that went into the production of the system. 10,000s of systems deployed in this field with faulty capacitors, and it's almost killed my $1 billion project, lifetime project. So when I went to the manufacturers and asked them, how come this component got into production? How come you didn't test the components? They told me that there's no such thing as testing components. They just bought it from a trusted source and gave me the documentation, and that's it. And the project was almost gone. Kind of frustrating. So this is when I knew what my next project's going to be. So it's kind of the reason why I went there.
Yeah, you're kind of getting even a little bit.
Yeah.
Right. I love it when businesses are started based on a personal experience. I think that adds a higher level of passion, a higher level of will to succeed, right? Because you can't let the bad guys win. And in so many products fall victim to counterfeit parts, and some never know, that they throw the part out. They just figure it was just a freak failure, and they never really know. So we're gonna dive into that. So you're the founder of Cyborg. The first question I was going to ask you, which I think you've already answered, is what led you to start that company? And of course, one of them was a little bit of revenge, and to make sure that doesn't happen again to you or other companies. Or at least it doesn't have to happen again to you.
Especially when you're developing a completely new technology or a new product. There's so many unknowns in development. And as a scientist or engineer, you always assume that the production side is perfect. So if there's a problem, it's probably my design or probably my technology or what.
Of course.
And you're not aware that your product failed not because of your design, but because of fraud. And this is really something that is really frustrating as a developer, because you're invested so much of you in a product just to fail because of something that's basic as read. So this is really something that is affecting everybody as a designer. If this is your product, you want to make sure that everything is good all the way. So what I learned from my experience is that it's not enough to have a very good design and even a very good prototypes, but to follow it up, make sure that it's been actually executed all the way in a good way, and all the materials that you use are of good quality, not just to assume that it is, but to actually check everything that you use.
Yeah, that makes sense. Some people think that if the counterfeit makes it in, the cost is you have to replace the product. But as your point was, the thousands of hours that one may put into trying to figure out what they did wrong, only to find out it was a 10-cent, capacitor or whatever the case may be. I think that's kind of a intangible cost. How do you put a cost on the engineering, the wasted time, the loss of reputation, all these things, not to even count the damage that may have been caused physically or otherwise, by a part that failed.
Yes, furthermore, today, in today's counterfeiting, there's an overlap between reliability and quality and counterfeit. So, for example, some people say that, okay, I will use a counterfeit component. If I don't detect it, it's probably a good counterfeit. So who cares? So it does the job, so it's okay. But in fact, this overlap between quality and counterfeit is devastating, because when you're using materials that you're not controlling, you're not sure what they're made of, the process is not stable, you're starting getting random errors, random failures, and you're not sure where they came from because the process is not good. My failure was from capacitors. Capacitors, like the simplest, cheapest components and very, very reliable. And the counterfeiting was very trivial. Someone took 11 years old reel of components, just replaced the label with a new label, and sold it as new. So it wasn't really a hard work counterfeiting, just replacing the label. And you make a quick buck, right? You sell this reel in $500 or something, and that's it. And your $1 billion project goes to trash. But the problem that happens was actually not something that you will normally trace back to counterfeit. You will say, okay, this is a reliability issue. This is a quality issue. This is corrosion, contamination. You don't think this is as a counterfeit. Because the problem was that components were old. So when they're old, their solderability is not as good as when they are fresh.
Right.
And the reliability of the bond degrades. So many of the quality issues that we have today are actually counterfeit issues that they would not have detected.
Right. Which brings me to the word counterfeit has one meaning in most people's minds, which is quite literally a fake part, a part which is not made by the person or the company you think it's been made by, etc. So we use the word counterfeit, though, to describe many issues. How would you categorize counterfeit components? You talked about relabeling, the date codes, for example, fake parts, real parts with wrong specs, used parts sold as new, sold as one brand but actually made by another. Totally, there's a classic definition of counterfeit, which is a fake product that's not real. There's nothing, it's a facade. There's nothing behind the shell. What are the different types of counterfeiting measures that you see out there, and perhaps maybe which are the most common?
Well, today you don't really see that facade case. It was common some time ago, but today when there's functional testing integrated into production, almost anywhere, this will be detected very quickly. So we don't see much of that. Actually, we never saw this. We scan over 2.5 billion components by now, and we never saw cases like this. What you do see very often are fakes, meaning that this was supposed to be made by one manufacturer, but in fact it is made by another one. This is very often something that we see. So we see old components sold as new, also very common, and we see components that their silicon parts were manufactured by the original manufacturer, but they are the failed ones from the wafer that were repackaged later on by a different source. So the silicon inside is original, only it failed. But still, although it failed, most of its functionality works, although on the lower level or the lower reliability. Be it because there's a defect there or because it was placed from a problematic area on the wafer. So this is also quite common. So I think this will be the main three ones. There is also another one, which is components that were recycled. They used to be much more common, especially in the crisis of 2017, 2018 with the Eyal CCs. But you see them also quite a lot. These are components that were old components that were removed from boards and then repackaged. Sometimes they go through blacktopping and remarking and resurfacing, and sometimes just as they are. So these are also out there. Some say it's more common, but we didn't see them that much.
There are a number of inspection methods designed to catch counterfeit. Some are perhaps more expensive than the counterfeit component itself. Some are destructive tests. So I'm glad the medical industry doesn't use that, that methodology to see if you have a disease. We're gonna kill you and then do an autopsy and figure out whether you were sick or well. And then there's other types of technologies. X-ray has been used to look kind of behind the facade or behind the wall, maybe to inspect the die or the wire bonds. There are a number of methods. Very few are being used en masse. I'm not aware of a 100% or even near 100% inspection protocol on components, whether incoming or otherwise. You may have changed that, which we're going to talk about. But the dilemma of inspecting for counterfeit is you quite literally are looking for a needle in a haystack. You're probably going to inspect potentially millions of parts to find hundreds of counterfeits. Perhaps. I don't know what the ratio is, but that's a costly endeavor. And in today's, not today. Today we're in a just-in-case environment in terms of purchasing, but in normal times when we're in a just-in-time environment, that doesn't really lend itself to incoming inspection to add one entire process before those parts can be used on an assembly. So there's a lot of logistical cost and practical roadblocks when it comes to inspecting for counterfeit. So much energy has gone into just making sure people don't buy counterfeit by vetting the supplier and things like that. We're going to get into some surprising stats on that in just a little bit, but I'll stick right now with the technology. You, through your company, have invented, it might be a good word because I don't think that technology had been used for that purpose before. But explain to me, walk me through what you're doing to detect counterfeits in this kind of novel idea that you guys came up with.
Right. First, you touched a really important point about is sampling components relevant as a screening method for components that you buy in the free market or from a relatively no trusted source. And the problem is that it's not. When even if you buy components from really honest brokers, and they are all honest, they're all trying to do their best to sell you good products. They don't know that they're using counterfeit components. They assume they're using good components, but they're not sure exactly, but this is what they try to do. So they are buying components from different sources, the leftovers, things like that. And then they reel it on the same reel and sell it to you because this is the component that you need. So by definition, a very large percentage of the reels that are being sold in the broker market are mixed by definition. So, and these are the ones that are being inspected. So if you're just sampling 1 or 2 or 3 out of a 3,000 or 20,000 lot, there's almost no way you're going to catch counterfeit because it's by definition mixed. So assuming uniformity, which is the basis of sampling, breaks. So this is why what we're trying to say is that you have to check all of them. Our philosophy is, suppose you could have looked at every component that you're placing on every board. Make sure that every component that you're using is okay. So it's not counterfeit, it's not refurbished, it doesn't have corrosion or cracks or defects or bent leads, because you look at them. Then you would use only good components, so your reliability will boost, because the difference between theoretical reliability and real reliability is huge. Why is that? It's a lot because of the components. You think you're using good components, but you're actually not. So if you would have used really good, authentic, qualified components, and you make sure that every component that you place is good to use, then your reliability and quality will boost, even if it's not related to counterfeit, even if it's just statistical issues that you have. So what we're doing is we're looking at all the components, and of course, you can't look by yourself. So we built an AI that does this for you. And the assumption behind this concept is that all the evidence you need about the authenticity of the component is out there on the surface of the component. There is information inside also. There is information that an X-ray can see, or the decapsulation can see, or there's information with electrical testing and electromagnetic and whatever. There's information all over the place. But just based on how the component looks like is enough to cover all the types of counterfeiting that we just talked about. For example, if the component is refurbished or was used before, it will look different from top side, from the outside. It will have different features. It will have evidence that it was reused. If, for example, this is an old component, you will look at the soldering lead and you will see that the condition of the soldering lead is more degraded, it's more rough. So this will give you an indication of the age of the component. If the component is a fake, so it was packaged by a different source, means that a different machine produced it, so it will have a different visual features on it. Think about it as forensic, like when you fire a gun, then you can tell from which barrel this bullet came from, because every barrel imprints specific features on the bullet. The same is with components. When you manufacture a component, the same machine is manufacturing all the components from this production line. So it imprints its features on this component. Now, of course, it's
like a fingerprint.
Kind of fingerprint. Of course, you cannot see it with your eye. You can if you do it well enough. And this is what they're doing in labs, trying to do one by one. But what we're doing is we're using the big masses of information and data to do this analysis. We're building AI deep networks that does this for all the components, so we can get to reliability of identification of the source of the component to over 99.9%, which no lab can do more than 90. So, and we're doing this on all the components.
So you're saying greater than 90% accuracy of detecting components? Is that? Or
what we're doing,
only
9.9% for most of types of the components. This is what we are doing, and we're doing this on every component that is placed on every board. I'll explain how we do it, but basically the concept is, imagine that you have a very large database of images. People like to use the word like a golden unit or golden sample. So we don't have a golden sample. We have like 20 million of them. So we're not using just one image to compare to another image. We're taking the 20 million that we have from this type of component made by this manufacturer, and we build an AI model that we can identify it. So if I give you an image of a component, the system already saw before 20 million components like this. So it knows exactly to tell the difference between a Murata capacitor and a Samsung capacitor. And that's the whole idea. Be able to tell the difference between different manufacturers using visual features from images of components. Now we need images. So what we looked for who's taking pictures of component in a production line. So at the beginning, we didn't find any. So we built our own machine, which is we built like a real inspection machine, which is a reel-to-reel machine. That is there's a reel in the entrance and there's a reel at the exit, and it goes through a camera. And the camera is taking pictures of all the components going from the reel to the other reel. So when you put a reel, you can take pictures of the entire reel. So we're using those images to take pictures of every component in the reel. So this is how we started, and which is actually a product that we have. It's called Kingfisher, but it is inspecting reels as they are coming into storage. Now, you don't want to check all the reels because you don't want to add this process to the manufacturer. So you're just checking the ones that are coming from brokers or from relatively not trusted source, which is also quite a lot. And you make sure that all the components in the reel are checked, not just one sample. And it is very, very powerful tool because you can make sure that they are authentic and you can find defects, and we are also decoding the marking on the top side to figure out if all the components in the reel are coming from the same lot code and date code, that are all coming from the same source and so on. And in many cases, they're not, because by definition, again, this market is mixed. So we see in a lot of cases where there are components, for example, you can see from in the same reel, components coming from the same manufacturer, but different manufacturing sites, different times completely, like one from 2020 and one from 2010. Things like this, all put in the same reel. Of course, there are counterfeits and there are defects. And so this is how we started. We're starting by using a machine that we built. Actually, we didn't plan to use this machine later on, but when the prices of counterfeit just started 2 years ago, our customers told us, "You told us there's a machine that can do that. So can I use it, please?"
Hey, you have to make it happen. Yeah.
Yes. So we okay, we'll make them. So this is the machine, but basically we're a software company, and what we're doing is we're using images to tell you what we know about the component. So the second stop is saying, okay, who else is taking pictures of machines? So we were in the show in Productronica, and we we met at the ASM, and we talked to them, and we realized they can be format that the SMT pick and place machine is also taking pictures. So when it's placing in the components, they're picking it up from the reel. And then there's a camera taking a picture from the bottom side in order to do the alignment. And only then it's placing it on the board. So here's our picture. So we can get a picture from the pick and place machine of every component that is placed, because the picture is taken of every component. So we're using the images of these components, and this is what we use as input. And of course, the volumes are very high because there's a lot of components being placed by the machine. So it makes the algorithm much more reliable and much more accurate. And also because this machine is looking from the bottom side, then we're getting the side that nobody is looking at, because everybody are looking also always at the top side, but we're looking at the bottom side. So on the bottom side, you can see the leads, you can see the shapes, you can see the imprints of the casting and so on. And all the things that the counterfeiters want you not to see. They're all on the bottom side. So it's very easy to authenticate and quantify component. And because we see the images, we see if the leads are good, and we see if we have corrosions or contaminations or mold, or there's all kind of bad things that you can see when you look from the bottom side. So that's the second source of images that we have. The third one is the images from the ERAI machine. The automatic optical inspection machine is taking picture of the board from the top side. And it doesn't care about the components themselves. It cares about the process. It wants to see that the component is placed correctly on the leads and everything is according to IPC and so on. Nobody actually cares about the components themselves. So what we're doing is we're taking the images there also, and we're verifying all the components from the top side. So we make sure that it's authentic. You can make sure that all the marking information is right, so you will have a good traceability information. Basically, that's the three different sources of images that we use to authenticate and qualify basically every component that you place on every board.
That's fascinating. Rather than reinvent the wheel and take pictures, you're using pictures that are being taken for another purpose anyway. Okay, here's a couple of points here. Going back to your earlier commentary on, properly vetting suppliers. I thought it was interesting. It's been reported that an estimated 15% of all spare parts purchased by the Pentagon turned out to be counterfeit. Well, I would assume that the Pentagon has some of the best vetting programs in the world, right? Maybe the Israeli Defense Force has an equal or maybe even better vetting process. I think the Pentagon has a very good vetting process. And the point being that even with the best of the best, with national security at stake, lives at stake, still 15% of parts are...
There's no technology to make sure of that. And military technology, it's even more dangerous because military systems use the qualification of a military product is very, very expensive. So if you're building an, F-35 system, to qualify every part costs millions of dollars. So after you qualify it, you don't change anything. Not at all. So what happens after 15 years? You're still making F-35s and you want to make this board and you have 10% of the components are obsolete or end of life. So you have to buy them from different sources, which is not the original manufacturer. So what I'm saying is that military is more susceptible to this kind of fraud than anybody else. So maybe this is why the percentage is that high. I think the
stakes are high, the prices are high. It's a sweet target.
Yeah,
you don't have to sell millions of parts to make your money.
And they have
to sell dozens of parts to make your money.
They have to buy from brokers because their components are obsolete. So they cannot buy it from original distributors.
Right. Okay, let's go back to the technology. You're hijacking pictures. You're hacking pick and place and AOI machines, and getting pictures out of it. First question: do you have to go in and modify one of these machines? Do you do that at the supplier side? Do you just talk to the supplier and say, we want access to it? Is that something that the customer has access to anyway? So how are you obtaining those pictures from a machine that's not designed to share those pictures?
Well, we're not really hacking them. We are working with the largest manufacturers of machine, which is ASM and Fuji, and also with Universal. We're now also trying to make more and more, but the two of them, ASM and Fuji, are number one and number three in the pick and place machine. And they built especially for us an API that exports the images to us. In the beginning, we did a kind of a hack, but now it's
just for proof of concept, right? For proof of concept, right?
The database in the algorithm, of course, together with them. Nothing under the table, but we built it at the beginning as a kind of a hack, and after we saw that it's working, and developed a tool for us. And so today, ASM machines and Fuji machines have this capability built in. So we don't have to change anything. It's a software solution. It doesn't slow the machine. It doesn't add any complexity. You don't have to buy any other module. So it's very simple.
It's there in the box, whether you use it or not. It's there in the box.
Yeah, I think in Fuji you will have to make some connectivity of cables, but just LAN cables connecting between 2 or 3 points.
Right. Now, these pick and place machines, particularly the brands you mentioned, are known for quite high speed.
Yeah.
And I want to throw out some numbers, maybe 30,000 parts an hour, maybe more.
And more, yeah.
So I'm envisioning in my head 30,000 photographs an hour, 30,000 comparisons an hour.
Yeah. Per machine.
That is mind-blowingly fast, because that's what you're offering is real-time detection of counterfeit, not like the board you placed 2 hours ago just came back with it's not like a medical blood test where you go out for a blood test and you have to wait a week to get your results, right? This is an instant. So all these technical questions come to mind. One is, I had read hundreds of millions of photographs that you guys have now in your inventory of images that you use for comparative purposes. So if I have a machine in Ohio, USA, placing parts, taking pictures of the bottom of these parts, and then sending them to some cloud, I would assume it would have to be a cloud-based system, because you can't. The pictures are so fluid that you can't just do a once a week download of the latest images. I'm sure they're quite fluid.
No, once a week,
and that would be a huge file. That'd be a huge file anyway, right? With the hundreds of millions of images you're comparing.
No, we're not downloading our database to every customer deployment.
Right.
First, currently we're not deploying dump mechanism. So let me explain. The best solution that we want to achieve, and this is something that we're starting to discuss with ASM and with Fuji, is the ability to tell the machine to dump a component if it fails the authentication or qualification. So we pick up a component, the machine, we take the picture, we have to now analyze it within about 50 milliseconds, and then tell the machine to dump it because it's corroded or it's broken, whatever. So we have to build this interface with the machine, and we don't have it yet. This is something that we want to do, but it's not there yet. However, the computation is already there. So the calculation is now fast enough to support it. But this kind of capability to allow dump, we will need to do the calculation on the edge. So next to the machine and not up in the cloud, because we will not be able to tolerate the delay from the machine to the cloud and then going back. So if you want to
that's what I was wondering.
If we want a machine to tell the machine to dump a component, then we have to have the calculation done on the edge. So that's a functionality that we don't have now. We do calculate fast, so we can get the results within the time frame that the board is still in the machine. But again, currently it's slower, but we're making it faster and faster. So the concept is not just to block every individual component, but to inspect all the components that you use. And for example, if we see a reel that has like 5 or 10 repeatable issues of quality of counterfeit, we'll just stop the machine and tell you, or of course, whatever you decide to do, either stop the machine or just alert. But it's customer's decision what to do. So we can signal you that this reel is bad. So you have to remove it from the machine because it's counterfeit or because it's poor quality. So this is one thing that we could do. The other thing that we do is we will let the operators, usually, and in the review PC of the ERAI system, we alert them that this component on this board is broken, but it's broken only from the bottom side. So they have an ERAI will not see it. So from the ERAI point of view, everything is fine. So I will give him an alert about this component, and I will show the picture, see this component, it's broken from the bottom side, or it's as corrosion or whatever. So the operator can replace this component and not let it go further, although the ERAI cannot detect anything. There's nothing to be seen from the top side.
Right. That's interesting. 50 milliseconds is the
50
time it takes to identify a part that doesn't meet a criteria.
Yeah.
Let's talk about the criteria for a moment. You have millions of photographs of images of what are considered good parts versus bad parts versus wrong parts, etc. What's the vetting process for the good stuff? What stops quote unquote bad stuff from getting into the wrong side of that database?
That's the hard part. That's the secret in reporting. I don't know how to call it. This is really the one of the most difficult things to do. How to make sure that your database is not contaminated.
Exactly.
So what you do is that you contaminate it once and twice and 3 times, and then you understand, okay, I have to do something different. And then you wipe everything out and start again. We did that a few times and we came up with some tricks and ways how to make sure that it is. Basically, we're using the fact that we have big numbers for that. So we're qualifying sources based on different locations, different countries, different suppliers, and so on. So this is all very verified, very, very changing sources and so on. So we can make sure that if this component is looking exactly the same from all these sources, and there's one that doesn't look the same, then probably the first one is the good one and the second one is the bad one. So we're using that basically the numbers. Second, we're looking for other attributes rather than the pictures, like let's say, for example, we have already, I think all of the manufacturers in a database, almost. So we already know, for example, how our Murata really looks like. It's not just by the individual component of and how they look, but also on the tolerances of everything in the picture. It's difficult to explain because it's not really a tolerance of something that you measure because it's deep networks. So it's not really something that you can measure. But just to explain, let's take, for example, one feature, which is not a feature that we monitor specifically, but let's say the length of the component. Okay, so we know that the length of the component distribution in a ring made by Murata is some kind of histogram. And so it has this height and width and so on. And we know that the histogram of Samsung is something a little bit different. So we're not just looking at every individual component, but we're also looking at the tightness of the production process that we already know for every manufacturer. So this also gives us more confidence to say, yeah, this fits Murata, not just by the way it looks like, but also by the tolerance reduction. So we have all kind of, this is just one concept, that we have a lot of tricks on how to do that. But this is really one of the most difficult tasks we had. And I'm happy to say that when you're processing over we're almost reaching 3 billion by now, components, then this becomes a secondary issue. This is very important when
3 billion.
3 billion.
Billion with a B.
Yeah.
Wow.
Billion.
That's mind-blowing.
Yes.
What happens when there's a legitimate change in specs? Like one company buys, we're in an incestuous industry, as you know, right? Everyone buys each other. So when one part was made by company A and now it's a TI part or vice versa, it's a legitimate part, but you have to be, your system has to be intelligent enough to go, that would have been a fail had that been a TI part, but now it is another brand part, another brand part, and fits the TI model, not the other model. So you know what I'm saying? I'm sure
exactly what you're saying.
That fly in the ointment happens all the time.
A lot of purchase and acquisitions, and there's a lot of changes, and there's a lot of things like this going on all the time. So we're handling this in 2 different ways. One, we don't have just one models for Murata. Just Murata has, I think, 9 production sites in Japan and at least 5 in China. So it's even Murata itself is using different location for manufacturing, so the components are not the same. So we're not assuming that all the Murata are the same. No, we're building clusters, and we're assigning names to clusters. So this cluster is Murata, this cluster is Samsung, and this one is also Samsung because it came from a different source. So we are managing it this way. So it's not uniqueness. This is one thing. Second thing is when we're getting an alert, for example, we're getting an error, an authentication alert. When we look into it, we see that this was supposed to be Murata, but it's something else. And then we find out that Murata acquired this company. Then we update the database to know that for now, this is also on Murata. So we have a database that is kept currently manually. So we add, whenever we find something that is changing in the system, we're checking that this change happened, and then we say, okay, from now on, this name and this name are okay. That's the idea, and it happens.
One of the questions I was going to ask you is, do you consider yourself a hardware company or a software company? But every answer you're giving me clearly indicates you are a software company,
Yeah.
which I think you had said earlier.
Yeah,
obviously, you have to have some degree of hardware to funnel that, the conclusions of the software through, right? I mean, there has to be I'm assuming there's some kind of box that sits next to the machine that
no,
just a modem, just basically a connection to the cloud.
what we're doing is very simple. When we're deploying a system, we need to have a server on site, and this is something that usually companies, CMs or EMSs has server. So we tell them, okay, we need a server or a virtual server, and that's it. And then this server is connected to the internet, so it's uploading the information to the cloud. And from within the site, it's connected to the machine through security stuff and to make sure that everything is safe. So that's all the installation that you need. So and we're not doing it. It's always the CM or EMS using their own hardware, and we're just telling them what we need, which is basically a server and internet and a secure internet connection. That's it. And then we install.
Is there ever a challenge? One of the ironies is it's the defense industry, the military industry, that has the most to gain from this type of technology, and it is the same industry, the defense and aerospace, military industries, that really don't like any connection to the outside world. The word cloud is a bad word in those environments. Has that been a challenge to convince them to kind of open a portal to somewhere else with a picture of every component they're using?
Well, actually,
I could see competing interests there.
Yeah, first it is a problem. It's something that is always hard for people to swallow, especially from the military industry. But we are working with military customers. It's working well. Some require that everything will be done on site, which returns to what I said, that we are working toward a project will allow us to run on real time. So we will probably have it in a few months, the ability to process everything on site. Of course, this customer will not contribute to our database, but we will be able to give him the value. Once every few weeks, we will download the models. Again, we don't have to download the entire database, just the models, which is not that big. So we will update it once for every few weeks. So everything will be up to date. And then we'll be able to give also service to customers on the edge without any internet connectivity, except for the downloading of the updates. So that's something that is also possible. But the whole concept is to give a solution that is completely software. We're also, by the way, we're also using the information we have not just to quantify components to make sure that they're in good quality and they're not counterfeit, but we're also giving traceability to the components in a level that is not done yet. Because even if you have traceability, that is the ability to tell for every board all the sources of the components that we have. Remember that we have picture of every component on every board from the bottom side and from the top side, with the results of all the analysis we did about corrosion, solderability, quality, authentication, homogeneity, and so on, for every component on every board. So this gives you a level of traceability that is not just date code, lot code traceability, but individual component traceability. Because the same way we're seeing every component being placed on every board, bottom side and top side. So we're using all this information as traceability information now. So for example, you think that you have assembled this part number, this dot code, and this date code, and this is what your system is telling you, if you have traceability system. We're seeing them. So every component that is placed on every board, we see. And if it has, for example, top marking, we can tell you, no, this is not the date code that you actually have. So even if you do have a recall, and you have to recall this component back from the field, you may be recalling the wrong thing. And for example, think about it, you have a failure somewhere in the field, your system is in Finland. You want to see how it looks like. You don't have to go to bring it back because you have pictures of all the components in the time of placement, top side and bottom side of every board that you're using everywhere. So this is like a completely new level of traceability. And the cool thing about it is you don't need to have any hardware. It's complete software. You don't have to add anything. So even if you don't have a traceability system at all, nothing in the site, no hardware, you can have level 4 traceability with only software. So this is traceability means that you really know what you're using. So even if there was an error or a counterfeit in the components that you use, you don't have to trust that. You only trust your eyes. You only trust what you see. So according to traceability, this is supposed to be a Murata component. No, it's a Samsung. So you think you have Murata, but by verifying it, you're having the highest level of traceability. There's also something cooler that we did. We did something to allow us to make this traceability, even to customers that don't have any traceability at all. Now, what we did is that it doesn't only have the data matrix code on the top side and the bottom side. So why do we need this, right? This basically is replacing the labels you need for traceability with a graph traceability level. So if you're using this, you're placing it as a component. So the pick and place machine is placing this as a component, and this gives you a serial number to the board. So even if you didn't have before traceability system, no labels printer, no labels reader, you can use this component to have traceability. Now, why is it related to us? Because we're a software company, right? Because we're seeing every component from the bottom side when it's placed. So when you're placing this component, we are reading the code from the bottom side. So we know to which component this serial number went. So we can give you traceability even if you don't have any hardware to support it. Because this alone, and the fact that we're reading the images for the bottom side, can give you serialization and traceability. And of course, when it goes to the ERAI station, the ERAI will take the picture from the top side, so we can correlate them. So basically, the idea is that you have a complete software solution and a level 4 plus traceability with zero hardware, and you don't have to do anything. We just look at all the components. Basically, the technology is to look at every component during the placement. Tell you
it's one of the data points that you capture the serial number of the assembly itself of the board, so that not only do you know that in real time a component is, let's call it good or bad, but call it bad for this purpose. But the serial number where the board was going to go on,
Exactly.
or the component was going to go on, is also captured. That I would think for counterfeit detection, that's less critical because it doesn't get on the board, but it benefits of just capturing the data of which serial numbers were on which board and things like that. Then obviously you need a whole nother set of data, which is the target that those components were placed on. So for traceability.
Actually, there's another trick in this one. The code on the top side and the code on the bottom side is different. And it's coded. What it means is that if you're scanning the component from the top side, it will read the serial number. And if you remove the component from the board and scan it from the bottom side, it will have a code. So it means that this component cannot be counterfeited. So if you have this component on your board, it will make sure that the entire board that you're using was not copied. So this is also got to do with counterfeit, because we got people telling us that we have failure in the field. People come with us with a board. We say, this is not our board, but we cannot prove it. So with this, you can make sure that this cannot be counterfeited. So this is the component that you actually placed on this specific board, and the top side and bottom side are coded. So it's also
That's interesting. It sounds like this is a solution in search of problems to solve, meaning that there are so many more problems that can be addressed with this type of solution that you're just barely touching, right?
You
know what I mean?
More time, I would tell you about the calibration of the machine and errors in placement, error bad pickups, and so on. Because once you start seeing the components that you use,
Right.
your eyes open up and you see everything which you're currently blind to.
Right. Well, it's like the old saying goes, it's amazing what you see when you look.
Yeah.
Right. Be careful where you look. One of the questions I had for you was, when you sell, I don't want to get into your sales method. This is not a commercial show, but when you offer this type of technology to customers, do you present it as an ROI model, or do you present it as an insurance company model?
No, ROI. But we're not.
ROI. Interesting.
It saves a lot of money both to the CMs and the OEMs. We're trying to we're selling our products to the OEMs. Although we are deployed at CMs, but we're selling our product to the OEM. We're using SaaS models, so it's based on how many boards we've inspected. That's the business model basically. And we find that the OEM people are one with the more pain. So the quality of the products is much more important to them. And just the fact that we can avoid even testing bad components or bad boards, and avoiding reworking and avoiding scrapping and avoiding quality issues in the future. And it saves a lot of money, both to the CM inside the production line or inside the factory, and of course also to the OEM, because you can reduce the recalls or the failure in the field rate significantly. Today the numbers are about, you're in the business for it, right? It's about 1.5% recalls or returns, or returns. And we can reduce it to about a half. And this saves a lot of money.
Yeah, you can certainly quantify that. Is this a subscription model, or is this one-time purchase model?
No, it's a SaaS.
Your database is constantly fluid, right? You're constantly adding data to it and probably coming up with more traceability models that you could offer. So what's the model that, if someone wants to do something like this?
Well, this is something that is new for this industry. We're using a SaaS model, so it's a software as a service approach.
Yeah.
So you don't have to pay anything for the deployment, or you don't have to pay as a capital equipment purchase or anything like that, or just per use. So per board that you're using, we're going to charge not a lot of money for every board, and basically that's it. So if you have a lot of them or less of them, you don't have to change anything.
Do you see your company rolling out relationships with other pick and place and AOI manufacturers beyond what you currently offer?
Yeah, we are. We are actively trying to work. We find that the best way to address them is through customers. So if a customer requests them, this is usually the best way to make them motivate.
Yeah, the customer voice is probably a little louder than your voice in their ears,
It's
right?
a technology company, but if the real customer comes in and say, "Hey, I need this," then it's done. So this is what we're doing. So we are trying to make to also be able to support other machines like Panasonic and Hanwha and other machines that we're currently pretty good with Fuji and ASM, which are very large. We're good with them, but I think our next aim is Panasonic, Yamaha, and Hanwha. This is for the SMT machine. From the AOI machine, we're working with Korean, Vicrox, ERAI.
Good one. Yep. And back to pick and place, is Juki on your radar too?
Yes, but only the new models with Juki, because the old models by Juki don't use cameras. They use lasers to do the alignment.
Interesting. I was going to ask you about that. I'm surprised to learn that even the modern cameras or cameras on modern pick and place machines would have a high enough resolution to do what you're doing with it. To look at the digital fingerprint, so to speak, or the physical fingerprint on the bottom of a component. I know they have to be high enough resolution to identify the leads and locations of the leads, for alignment purposes, but they don't need any more than that for their purposes. So I was surprised to learn that the cameras on the machines don't have to be upgraded, or at least there was no mention of it having to be upgraded in order to use your technology.
Actually, we share the requirements with the machine because they want to be able to place the component very accurate. So they have to make the measurement very accurate. So the lighting has to be perfect, and the zoom have to perfect, and the focus have to be perfect, and everything is already tuned to make a very accurate measurement by the camera. And also the resolution of the camera, which is about somewhere between 10 micrometers for the best models to 25 for the oldest models. In a way, we're good with that because we should have enough pixels in the image to make it work. So either way, it's suitable for our requirements. So even for 0201 or 01005 capacitors, we have enough resolution to have very good models. And by the way, this is a good. We're very sensitive to the quality of the picture, of course. So if, for example, we're getting images of completely white components because the lighting is bad, or components that are out of focus, then of course we cannot process it. So, but this is not a bug. This is actually a feature, because what we're doing is we're telling the machine operators fix this bug, because this is costing them a lot of money. Because if the lighting is bad, then the placement is not accurate, and the attrition is
Sure,
and the tombstone is 10 times higher, and so on. So we give them this information back as feedback, so they will be able to tune their machine better, and we tell them exactly where the problems are. So in which component the programming is wrong, in which component the height is programmed wrong, so the focus is bad, and so on. So it helps us. We're getting better pictures out because of that. They're getting better process because of that. So it's really a win-win. We're also seeing if there, for example, the components are being picked up not stable. So sometimes it's like this, sometimes it's like that. We're also, if there's dirt on the nozzle, we also see it. We give them a lot of information like this, which helps them improve their process. And this is why CMs love this system.
yeah, it sounds like it. A lot of possibilities beyond its original intended purpose.
Yeah, once you look at the compliance, you cannot stop.
Exactly. Yeah, it's a slippery slope. I think you guys are going to be busy coding 24 hours a day. So do you see a time, maybe this is happening already, but do you see a time when the component manufacturers will submit photographs that meet your criteria in terms of quality of known good parts? So rather than experiencing good parts through millions and millions and millions of photographs, without reported problems, you actually get a preview of a part, or you get an official source from the manufacturer. Would that be a benefit, or is it better the way you're doing it now?
Yes, we didn't want to be dependent on this information, so we built the system without this.
Yeah.
But there is something interesting that we can give the manufacturers, because we see the components at the time they are placed, so we can tell them what's the quality of their components and when they're placing, so they can see that their supply chain, for example, is good. Because if you see a lot of corrosion or a lot of defects or problems, then it means that the product didn't survive well until the time it was deployed to be operating. So this we found that we got some interesting feedback from components manufacturers about that. Said, wow, this is how my component looks like during placement. So we can tell them, yeah, this is like supposed to be 6 years old, but look at the corrosion on this. It's like a 10-year corrosion. So this is interesting information for them. So this is one interesting parameter. The second thing is, because we're seeing so many components from different sources and different date codes and different manufacturers and so on, we can measure and quantify all the parameters about it. So when you are purchasing a component, you can make a smart purchase. Let me explain, for example. If we see that, for example, the dimension tightness within a reel of one manufacturer is, 0.1 millimeter, and another one is 0.4 millimeter. And as a designer, you want to use the one that uses the tighter or wider according to your requirements. So the idea is to get feedback from real measurement in real components, rather than just specifications that are roll-up, that are just what they're supposed to be. Let me give you an example. There are some manufacturers that mix within the same reel two internal lots, which is okay, it's legitimate, but the difference between the two lots within the reel may be very large. There may be within the same reel, the difference between the smallest one and the largest one will be 0.3, 0.4 millimeters on a 1 millimeter component, which is a huge difference. So if you are placing it coming from the same reel, placed on the same board, they may cause problems, because the differences are maybe causing issues. And it actually causes issues. We have seen examples like this. So getting this information and sharing them with the designers or the API people may be valuable from the design point of view. But also, not just from design point of view, but when you buy a component today, you're just buying the component based on availability and price. You don't have any quality parameter. Say, for example, if I would tell you that the average defect rate of one manufacturer is, 100 ppm, and in another one is 10 ppm, today it's not considered as part of the purchasing, but this costs you a lot of money in production and reliability. And today it's not a parameter, but we're measuring these parameters, because we're saying that what is the DPM, the defects per million, for corrosion, for body defects, for bent leads. All of this is measured. So when you're buying a component, you can buy it not just based on availability and price, but also on the expected quantity that you can get. So this is also something that we include the components manufacturer. And of course, the components manufacturer want to get this feedback about the quality of the products as it goes into deployed on the boards.
Yeah, excellent. Final question, Eyal, before we head our own ways. Get out your crystal ball. Where do you see the counterfeiting industry going? It's interesting. We never say counterfeit prevention. We always say counterfeit mitigation. You know, it's. I don't want to put words in your mouth. What in your mind is the future of counterfeiting? How much do you think we can reduce it? Where's it going? What are the counterfeiters doing? How will they discover what you're doing and try and come up with workarounds for it? Give us your predictions.
I think that once you start looking at all the components and using deep networks and AI technology and big data, it's a huge step in combating this. It's like the difference, remember in the old days on the computer viruses, there were computer viruses and you avoided them by separating disks and stupid thing like this. And then came the antivirus and the battle changed completely, or the firewall. So if you don't have a firewall or you don't have an antivirus, then you're dead, right? So once the technology that can really address the problem is available and it's very easy to use, I think this is going to make a huge change. So the next step for counterfeiters will take years. And of course, there will be
a few years ahead of them. Yes, you're a few years ahead of them. But then by then, hopefully, your technology will evolve even more beyond its current capabilities. And it's a battle. It's a race between the bad guys and the good guys.
The same technology can be applied on any measurement, basically. When we started, we thought, we're not sure that the image is going to be enough. So let's look also UV spectroscopy and visual spectroscopy and higher spectroscopy. And maybe do X-ray and do electromagnetics. And we did all of those, except X-ray, because it's more complicated. So we did all of this. And we found out that, yes, you can do it also with the other things. But the simplest method was to use images. But the quality was overwhelming. So we didn't have to go to electromagnetics and we didn't have to go to higher spectroscopy. But if the counterfeiters will ramp up, then we will ramp up also.
Well, as you're ramping up, we're going to ramp down and conclude this conversation. Dr. Eyal Weiss, thank you so much for being my guest today. What you're doing is fascinating work. I find our entire industry quite fascinating, but not every company is actually doing something that provides quite as much value to the industry as yours. So thanks for the work you're doing. Go get them. Get the bad guys. Get your pound of flesh. You're owed that from your last experience. And I wish you not just success, continued success. I appreciate you carving out the last little over an hour with me and sharing with me and my audience the novel technology that you've introduced. And I think it has an awful lot of potential and current use, not just potential, but it has a lot of current use. And I wish you all the success in the world with it.
Thank you very much. It was a real pleasure. Although everybody already went home here.
Yes, you're in Israel. I'm in California. We couldn't be too much farther away, but I still have my whole day in front of me. So you need to go home and eat dinner.
Yeah,
I appreciate you staying late and being the last one to turn the lights off.
Thank you very much.
Well, that's another episode. Thanks for listening or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, and on our newest channel, Amazon Music, or virtually wherever you get your podcasts. And a special thanks to Circuit Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating the show. Thanks for your questions and episode suggestions. Please keep them coming. They're very helpful. Send comments or episode suggestions to Mike at mikeconrad.com. That's Conrad with a K. And be sure to subscribe to the podcast on your favorite podcast app. If you're watching this on YouTube, click the subscribe button and the bell icon to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday each month. Once again, thanks for listening or watching. Stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.